Good morning. Today we will have the second part of the lecture on ensemble learning. In the last class, we gave a introduction to the different ensemble learning methods. Today I will talk about two specific methods, bagging and boosting, which are methods for ensemble learning. Bagging is a method for ensemble learning. Bagging stands for bootstrap aggregation. So, we saw that in order to use an ensemble of learners and be able to combine the learners and get better accuracy, what is needed is a set of learners which make independent errors. We want a set of learners which make independent errors, and we discussed in the last class, in order to force the learners to make independent errors, you can make them use different samples, data samples. You can make them use different parameters of the algorithm, or you can make them use different algorithms, and the output can be combined by some form of voting. Now, in bootstrap aggregation, what is done is that first of all, the samples are generated such that the samples are different from each other. However, suppose you have a training set S, or let us call it D, and if you are going to have n learners, or let us say k learners, you could split the training set into k partitions and use one for each learner. However, often it is the case that the size of the training set is not large. So, if you make it smaller by splitting it into k different sets, the individual training sets will be small. And as we have observed while talking about the foundations of machine learning, is that if you use a learner on a small training example, the learner can overfit, it can have high variance, and it will not generalize well. So, we want to be able to use, we will not be able to afford to have fully independent data, but we can sample randomly from the data, so that there may be some overlaps, and we do that by a method of sampling. Instead of dividing it into k disjoint groups, we treat this as the pool, and from this pool we sample D1, D2, D3, Dk. So, these are the different data subsets which is sampled from the original data. They may have some in common, but they also will have different values. Now, as we have discussed that, so what we do is that to get DI, draw random samples with replacement. For example, if we desire that each of these DIs will have m examples, we randomly draw m samples from D with replacement. That is, we can have the same instance repeated several times, and some instances may not appear in a particular DI, and so these DIs can be different. We have discussed in the last class that in order that ensembles will work, we desire that these learners may have high variance, and by combining these k learners, we can reduce the variance in certain cases by 1 by k. So, we can start with learners with high variance, and we also discussed that in order that the different learners produce different hypotheses, we want the learners to be unstable. Stable learners, irrespective of what data you get, the output will be similar, that is, they have low variance. Learners with high variance are unstable, among the algorithms that we have studied, decision tree, then neural network, they are unstable algorithms. Decision tree, neural network are unstable algorithms. Given different data, they may give different models. Whereas algorithms like k nearest neighbor is more stable. So, when we want to use ensembles or specifically bagging, we wish to use unstable learner. And we use bootstrapping to generate the training sets. We generate these k training sets. And we train, so once we get these training sets, so suppose in this D, we have the instances 1, 2, 3, 4, 5, 6, 7, 8, right? And we sample and we get D1, and D1 may have 1, 5, 1, 2, 3. And D2 may have 6, 1, 6, 5, 4. D3 may have 4, 1, 5, 1, 1. So, we get these different learners, different data sets, and we train a learner L1, L2, Lk on these different data sets, and we get a model. And these models have to be combined by voting. So, we use bootstrapping to generate these k learners and train a base learner with each and combine the output by voting. So, in bagging, what we do is that we do sampling in order to get these individual data sets. We do sampling with replacement. And from each sample, we build a bootstrap sample, and if you look at each instance in the original data set, what is the probability that it is included in the sample? Suppose there is a sample of size m, a sample of size n, right? And suppose this data set is also of size n. So, if you take any instance, what is the probability that when you draw randomly from this data set, from the sample, what is the probability that a particular instance will get included in DI? It is 1 minus 1 by n. And if you do n such draws, so if this is n, size n, and each of the samples are also of size n, then this is the probability that a particular instance will get included in the sample. Okay. And so, this particular sample will get selected, and we can see that this can be approximated by E inverse, and we can see that if we use n random samples, about 63% of the instances, about 63% of the instances will occur in each of these samples, 63% of the unique instances, and other instances will be repeated. This you can find out. Now, so this is about bagging. Next, we come to a second ensemble algorithm, which we call boosting. Now, in bagging, we are generating the data samples D1, D2 from the original data set, and they are all getting the same probability of getting included in any of these subsamples. Now, in boosting, what we do is that again we have a sample. Now, when we try to get DI, we have to sample from D. But now what we do is that we assign a probability with each instance. So, every instance is assigned a probability. Suppose to start with there are n instances, and initially we may have we may give equal probability to all the instances. So, each of none of them has a probability of 1 by n. So, in the first iteration, you choose D1 based on this uniform probability distribution, and you get D1 by sampling. Now, on D1, you train a learner L1, right? And this learner you apply to all these instances. Now, this learner may have 100% accuracy on these instances. If that is the case, then it's a very good learner, you don't need to really proceed. So, it will have, all of them it will do correctly. But in most often what will happen is that this learner will label some of these instances in D correctly and some wrongly. Now, suppose D1 labels this correctly, labels this wrongly, labels this correctly, labels this correctly, labels this wrongly, labels this wrongly, labels this correctly, labels this correctly. Now, what we want is, we want the next learner to have independent errors, and we want the next learner to do well on those instances where the current learner has not done well. So, now what we will do is, we will change the probability distribution, and more specifically, we identify those instances which were wrongly labeled by learner 1, and we will increase the probability of these instances, and those which were correctly labeled, we will proportionately reduce the probability. So, what we are going to do is that we want to hike the probability of those instances which we were not correctly classified by learner L1. And so, we will have the same data set, but now the probability distribution will change. Now, we will now sample D2 according to this probability distribution, and we will get a subsample, and this subsample is more likely to contain 2, 5, 6 than 1, 3, 4, 7, 8. Okay? So, we get D2, and on D2 we apply the learning algorithm and get the learner L2. Now, again we apply L2 on these training instances and find out which ones D2 does error on. Suppose D2 wrongly classifies 2, 7 and 3, and the rest it does correctly. So, what we are going to do now is to increase the probability of 2, 3 and 7 beyond what was the current probability, and reduce the probability of the rest to keep the sum of the probabilities equal to 1. Okay. So, based on that, we are going to find D3, on which we are going to train learner L3. Like this we will go on. We will get the different learners, different data and the different learners, and then we will combine these different outputs of the different learners by voting, and while voting we will assign a weight to each learner, and the weight will be somewhat related to how good the learner was. So, this is the basic boosting algorithm. So, in boosting is an iterative procedure. We start with a uniform probability distribution on the given training instances, and we adaptively change the distribution of the training data. So, initially all the training instances have equal weight. After each round of boosting, the weights get changed. So, we learn a hypothesis or learn a learner, and we assign a strength to each learner. We assign a strength to each learner, and this strength is used to decide the weight of the voting. And the final classifier is a linear combination of these different learning hypotheses. weighted by these weights. So, what we require is that the individual, what we have said earlier also, the individual learners may be weak learners, they must be unstable, they may be weak learners, in fact, it is better if they are weak learners, but they must have more than 50% accuracy for a 2-class problem. Now, there are several boosting algorithms. One most common algorithm for boosting is Adaboost, which I will talk about in today's class. So, we have seen that boosting can turn a weak algorithm into a strong learner. So, Adaboost takes a sample as input, and let us say we call this sample S, and it has it contains x1, y1, x2, y2, xm, ym. This is the training example. X is a vector of the input attributes and y is the output attribute, right? And we have a weight for each training example. Initially, d0i is the weight of the ith training example. Initially, d0i equal to 1 by m for all I between 1 to m. Initially, at time 0, all the learners have equal weight, which is equal to 1 by m, and we use a algorithm. Now, we do capital T number of iterations. In the first iteration, we construct d1. On x1, x2, xm, we construct d1, right? And by sampling from this S using the distribution d0, right? So, let us write it as script d. So, this is d0. So, we get d1, or let me call this s1. Then what we do is that we update d1. So, for those I for which from S1 we get a particular learner L1. So, we find out which training examples L1 classifies correctly. For those training examples that L1 classifies wrongly, we increase d1i. d1i is increased for those examples on which L1 wrongly labels, right. So, we update d1i, and from d1i we sample S2, and from S2 by running our algorithm we produce the learner L2. And let us say when we apply the learner L1 on S, the error is epsilon 1. When I learn L2 on initial S, error is epsilon 2. Similarly, S3 produces L3 with error epsilon 3, right. So, epsilon t is the error over the current sample. This is the error not over the original data, but over the current sample. Epsilon 3 is the error over S3. Okay. Now, with this, let us just please look at the slide to the boosting algorithm. So, we are given S equal to x1 y1, x2 y2, xm ym, where x is the set of input attributes, y is the output attribute, and initialize the distribution to 1 by m. We initialize the distribution to 1 by m, and then we run this iteration for t equal to 1 dot dot. So, we train the weak learner using dt and get a weak classifier. Let us call it ht. Then we choose alpha t as the weight associated with ht. We will see later how alpha t is chosen, and we update the distribution. So, we get dt plus 1I as the updated distribution, which is obtained from dti into exponential of minus alpha t yi ht xi. So, yi is the target output of the particular training example I, and ht xi is what is output by the learner ht, right. So, if they agree, this is 1, if they do not agree, it is minus 1. Okay. So, divided by a normalization factor. This normalization factor is chosen such that the sum of the probabilities, sum of this overall I is equal to 1. So, Zt is a normalization factor. Now, we do this capital T number of times, and final classifier that we output is given by Hx equal to the sign of sigma alpha t ht x. So, h1, h2, ht are the different classifiers that are output, and ht are the different classifiers. They are weighted by alpha t, and the total is computed. If the total is positive, then the class is positive. If the total is negative, the class is negative. Okay. So, this is the basic Adaboost algorithm. You can see the slide here where the algorithm is given. So, this is our sample. yi is either minus 1 or plus 1. This is the initialization of the probability distribution, and we run this algorithm for capital T number of iterations. In each iteration, we use the current probability distribution to generate the data, and on that data we train a classifier ht. We find alpha t. I will show you how alpha t is computed, and based on that the new probability distribution is computed, which is dt plus 1I, and Zt is the normalization factor. So, to make sure that the sum of this is equal to 1, and the final classifier is taken as a vote of the different HTs weighted by alpha t. Now, let us see how alpha t is computed. First, we need to compute epsilon t, which is the error of the hypothesis HT with the current sample. So, epsilon t is summation over the training examples. DTI is the probability of the ith training example in the sample, right, and delta HTI not equal to yi is, if I is misclassified, this is 1, otherwise this is 0. So, what I am doing is that we are taking the number of misclassifications. Each, we are taking the weighted sum of the number of misclassifications weighted by the probability, right. So, that is epsilon t, and alpha t is computed as half log of 1 minus epsilon by epsilon. So, this epsilon is a measure of the error, and alpha is a measure of the accuracy of the particular hypothesis HT. And in the ensemble, when we are combining the votes of the different hypotheses, we are combining based on alpha t. So, this is the mechanism which is followed by the Adaboost algorithm, which is a very popular ensemble learning algorithm. Now, we will talk about a little bit more about why this ensembling works. So, if you are given a number of weak classifiers, they can be combined to get a strong classifier. These weak classifiers must have error better than random. That is, epsilon t must be less than 0.5 for a 2-class problem. It can be shown that this algorithm Adaboost will achieve 0 training error exponentially fast under the assumption that the errors are independent, errors of the different hypotheses are independent. It is shown that 1 by m, this is the average error, delta hxi not equal to yi, I equal to 1 to m, this is the average error. It can be shown the average error of this ensemble produced by Adaboost is less than equal to the product of over all the members of the ensemble. This is the product of all the learners that we are using in the ensemble times zt, which is less than equal to exponential of minus 2 small t equal to 1 to capital T. This is the total number of iterations in the Adaboost, half minus epsilon t whole square. So, epsilon t, as I said, has to be less than 0.5, right. But even if it is a small number, it need not be very much smaller, but whatever it is. So, this is the half minus epsilon t is a fraction less than 1, and as you take this product, this this will become, as t increases, this will drop to 0 exponentially fast, and therefore Adaboost can this algorithm, if the learners are independent, it can become very good as you increase the number of iterations, right. So, we are not going into the theory, but this is a result which has been proved. Now, we will show, please look at the slide, we will illustrate Adaboost, how it works. So, suppose this is the initial data. We have 10 data points, 5 of them are positive, which is given by green, given by blue are positive, and the 5 green ones are negative. And all of them, each one of them has probability 0.1. The sum of the probabilities is 1. Now, when for boosting, you select the first set of training example, and the ones within squares get selected, right. So, these are the data points that you use for training, and based on this, you get a classifier, and this classifier, let us say, predicts these 3 as positive and these 7 as negative. So, we see that these 3 are correctly labeled as positive, but here these 2 are wrongly labeled as negative, right. So, now this probability distribution is updated. So, these 2 where Adaboost makes an error, their probability is boosted using the formula of boosting, and they get boosted to 0.4623, and to balance this, the probability of these 8 examples are reduced and they become 0.0094. Based on these values, the value of epsilon and alpha can be calculated, and alpha happens to be 1.9459. Now, what happens is, the next round takes place. In the next round, we have this new distribution from which the data points are sampled, and let us say now these 6 points which are in square are sampled, and suppose the learner that you come up with is B2. Now, B2 again makes some error, and based on that error, B2 makes error on these 3 examples, and based on this, the probabilities of these examples are increased and the others are reduced, and alpha in this case is computed to be 2.9323. Then the third round takes place on this new distribution, and let us say third round chooses some samples, and B3 is this classifier, and there is an error on these values, these middle values, and so error on these values. Based on that, the probabilities are recomputed, and alpha is now computed to be 3.8744. Finally, these three classifiers are combined with alpha 1, alpha 2, alpha 3, and the overall classifier now is able to label these as positive, these as negative, this as positive. So, in this particular case, boosting is able to combine these three classifiers into a classifier which is fully accurate. It may not always happen that you get it something fully accurate, but what is interesting, you see that these classifiers were linear classifiers, they just made a division of this interval, whereas the ensemble classifier does not belong to the same type of classifier. It is able to identify that there are positive examples here and negative examples here. So, this is an illustration of the Adaboost algorithm. With this, I stop today's lecture and on boosting. Thank you.